quantum mechanics. So in previous lecture, we have already seen that how the kinetic energy and linear momentum operators were commuting with each other. That means the commutator of linear momentum and kinetic energy operator was zero. So in today's lecture, we will see about the commutation of the position as well as the kinetic energy operator, right? So let's try to understand these things. When we talk about the position operator, we denote it as a capital X, and the position operator, this is your position operator. And then kinetic energy operator, that is the T cap, we have seen that this was equals to minus h square divided by 2m and del 2 by del x square. So this is the second differential in x. So today we have to check whether this kinetic energy operator and position operator and kinetic energy operator's commutator, that can be written as x t cap of psi minus t cap x of psi, t cap x psi. So I'll write both of these part separately. So first I'll start with x t cap of psi. So if I write this thing, so it can be written as x t cap psi. So it can be written as, let's say, x, and what is t cap? T cap is equals to minus h square divided by 2m and del 2 by del x square, and this will be psi. So when I talk about, now you got this function after operating the kinetic energy operator over a wave function psi. Now this position operator will operate over that function that you got from the operation of the kinetic energy operator over the wave function, and this is just a multiplication of this minus h square divided by 2m, and this will be del 2 psi by del x square. So finally, if you will see this value, so you will be getting the result of x t cap psi, that will be equals to minus h square divided by 2m into x del 2 psi by del x square. So let's say, assume this one is my equation first. Now I'll talk about how this t cap x psi operates. So if I talk about these things, then I can write t cap x will operate over a wave function psi first, and that can be written as your t cap. This will go like x of psi. Okay. Then I'll operate this kinetic energy operator minus h square divided by 2m del 2 divided by del 2 by del x square, and this x psi. So here you will be getting minus h square divided by 2m. So it will be x del 2 psi by del x square. So this is just a simple second order derivative, and you have to operate separately, like we'll separate x over psi and then psi over x, plus you can write psi, and if I do del 2x by del x square. So if I do these things, this part will become equals to 0, and finally you will be getting this value minus h square divided by 2m x del 2 psi by del x square. So this one is my second equation. So from here you got that operation tx psi, that is equation 2. So now let's check about equation first and second, and how or what kind of value you are getting after the operation of this operator here over a wave function psi. So if you do this operation here, then you will be getting the x t cap psi minus t cap x psi, that will be equals to minus h square by 2m x, this will be your x del 2 psi by del x square, and then this will be your plus h square by 2m x del 2 psi by del x square. So you should see this will get cancelled out, and finally you will be getting x t cap psi minus t cap x psi, that will be equals to 0. That means x t cap minus t cap x psi that is equals to 0. And what do you mean by these things? This is just a commutator operator that is operating here. So I can say that x t cap minus t cap x that is equals to 0. So you can use this operator x t cap that is equals to 0. This result clearly tells you that the position and the kinetic energy operators are commutating with not commutating with each other, because this is equals to 0. And if it is equals to 0, then what will happen? If you have commutating with each other, and if you have a common eigenfunction, then you can calculate the position of the particle as well as the kinetic energy at a particular location simultaneously. And this is what the result is. So in the next lecture, I will be talking about the expansion of the operator and how can you operate this kind of operator. Like let's say if you have x plus 1 whole square, or if these kind of operators are there, then how can you expand this operator, and will operate this kind of operator over a wave function. Okay, thank you.